So far we've been talking about conservative forces, the ones that conserve energy, or that have path independence between 2 points of the work done, or the work around a closed loop is zero, any closed loop. Non-conservative forces are, of course, forces that aren't conservative. So non-conservative forces don't conserve mechanical energy. Instead, they change the energy state of the system. They're how you get from one energy state to another. The potential and kinetic energies are essentially internal, and they can redistribute energies among parts of the system, but they can't increase or decrease the energy state. A non-conservative force may be dissipative, like friction, reducing the mechanical energy by, for instance, turning into heat. Or a non-conservative force may be additive, increasing the mechanical energy, such as muscles doing work on a box that you're pushing. If there are both conservative and non-conservative forces acting, then the total work is just the sum of the work done by each type. In other words, all the work has to come from either the conservative or non-conservative forces. There are only those two types, right? It's a complete dichotomy, and so it must be one or the other. But remember that the total work is the change in kinetic energy, and that stays true. The change in the mechanical kinetic energy of a system is the total work done on that system. And then the work done by conservative forces, we said, helps define the potential energy such that the work done by conservative forces is minus delta U. So these are the same thing. And these are the same thing. So we can say that we can solve this over, and we can say that the work by non-conservative forces is delta K plus delta U, which means it's delta of K plus U. But remember that K plus U was the mechanical energy. So we end up with the very important result, and stated earlier, that the work done by non-conservative forces is the change in the energy state of the system. That's how we change the energy in the system. And vice versa, if we see a change in the energy state, there must be at least one non-conservative force doing work. So to see how this plays itself out here, let's do an energy bar graph. A 100 Newton box is initially 0.4 meters above the surface of a table and is moving upward with kinetic energy of 80 joules. A man is applying a constant upward force of 80 newtons with his hand to the box, as shown. Complete the energy bar chart for the earth box system before and after the box is moved upward a distance of 1 meter. Put the 0 point for gravitational potential energy at the surface of the table. So important things. They don't give us freedom. We know where the 0 is. Because the 0 is there, when we have something which is this far above, it will have some energy. Remember that the potential energy is going to be mg times the coordinate, but notice that mg is the weight. So really we're talking about the weight times the coordinate. The weight is 100, the coordinate is 0.4, so we end up with 40 joules of potential energy. We were told that the initial kinetic energy is 80. They told us that. And notice that that's 1, 2, 3, 4 of these little bars. So each bar must be 20. So we must have that amount of initial potential energy in gravity. Then this asks us for the 0 of the spring energy. There's no spring in the problem, so the energy is 0. Is there external work done? Yeah, the person, the man, is applying external work through that force that he's using. So we can say, well, the work done by non-conservative forces is their force times their distance. So here we have 80 newtons times 1 meter. So that's 80 joules, as big as the kinetic energy. All right, and then we get to the new spot. We are 1.4 meters above the table, so that's 140 joules of kinetic energy. Since each bar is 20, all right, it's 140. So we must have 7, wrong place, 140, and we have 7 bars. And we can compute that just because we know where it is. We are aware the spring is still 0. And so we have over here, we have 120 plus 80, or 200 joules of available energy. Over here, we've spent 140, so we must have to have 60. which is 3 of these. All right, in other words, does that make sense? Well, let's say we have, let's look at what happened to our potential energies. We need to add 5 to this potential energy, so we take, we can take these 2, or actually I guess we can take all of these 4 to go over here. But that's not enough, so we also had to take 1 more. So this ends up being only 3 high, which is what we have.